of architecture. He will give us a presentation about green building. Professor Han?
Yes, thank you.
Okay, thank you. The floor is yours.
Okay. Yes. Thank you. I'm honored to have the chance to share my works in this workshop, and my presentation will cover the following aspects. The first part is about the background and the public's requirements for the healthy quality of the human settlement environment have continued to increase. At the same time, the green performance of buildings also shows a trend of compound development. And the continuous improvement of green building design standards requires architects to fully tap the potential of building green performance optimization and pose new challenges to architects. We need to have stronger multidisciplinary data integration capabilities in the early design stage and explore the possibilities of architectural design from a broader perspective. Besides, we have to realize the trade-off of multiple building green performance, which has increased the difficulty of making design decisions for green performance optimization. Facing these challenges, we try to couple the AI algorithm and tools in architectural design. And as an interactive between indoor and outdoor environment, building facade is an important system, and our study is focused on the adaptive facade. That's because the rapid development of technologies such as fifth generation communications and the Internet of Things have provided development opportunities for adaptive facade. The environmental response mode of the building facade changes from static to dynamic. And the optimization design of adaptive facade needs to consider the dynamic characteristics of its response to the environment, which further increase its complexity. To improve the optimization accuracy and efficiency of adaptive facades, we explored building information modeling, performance simulation, and decision-making support methods, and proposed several tools. And the building information modeling tools has experienced multiple generations of development and has achieved the integration of multiple information, but its modeling efficiency still needs to be improved. We applied parametric modeling technology to integrate multiple types of building information and developed a design tool based on the Revit platform. And besides, precise urban context modeling is the basis for evaluating the green performance of building. And the original drawing and field measurement method cannot obtain the geometric information of the surrounding environment, such as vegetation and public facilities, accurately and of great labor cost. Therefore, we explored the method to to model urban context automatically based on the UAV photogrammetry, which goes from image acquisition to the image-based reconstruction, and to end with the estimation of green performance of buildings. We can find that as the level increase and the details of the buildings are enriched, and a comparison of annual solar radiation with or without urban context was conducted. The results show that the shadow of adjacent buildings, vegetation, and urban facilities seriously affect the solarization acquired of the building facades, and the magnitude is depending on the season. And the building performance analysis and standards changed the way in which buildings are designed and operated. After decades of development and of building performance simulation tools, a huge family of simulation tools has been formed, realizing multi-performance simulation of wind, daylight, thermal, and energy consumption, including 3 types of method: the white box, the black box, and the gray box. And however, the evaluation of different design and operation options is becoming more time-consuming and computationally intensive than ever before. Also, building dynamic simulation tools are potentially a suitable way for accurately assessing the energy performance of buildings and other green performance of buildings. They require adequate training and a careful evaluation of model input data. In response to this problem, we explored the machine learning-based building performance prediction method, and we trained the artificial neural network model with data samples to establish the mapping relationship between the architectural design variables and the green performance. And although various artificial neural network model has been proposed for the green performance prediction, and most of these models are have critical generalization limitation and often difficult to integrate in existing design workflow. Hence, we try to improve the model generalization capability by feature engineering and hyperparameter optimization. The spatial relationship is defined by including sensor point local coordinates as input, and hence the model can predict the daylight performance for any point on the working plan instead of a few predefined ones. And the results indicate an overall good fit. The high resolution prediction result matches the simulated values closely, despite the higher error near the walls and corners. This is due to the lack of samples in original training set and can be remedied by adding higher resolution training data. We also proposed a design platform for multi-objective optimization design, which can realize automatic performance evaluation and statistics of building and surrounding information. The third part is a case study, and based on the functional requirements and the regional characteristics of the severe cold region, the optimized design was carried out for the disadvantages of the green performance of the plant, with the aim to retrofitting it into an open office. This is the adaptive facade system, which is optimized in this case study. And it is designed to improve the daylighting performance while reducing the risk of glare in the office area and alleviate the heating load in winter. The adaptive facades generated also present a rich sense of rhythm in the form, and a virtual sensor matrix is set in the simulation model to calculate the target data for indoor daylight environment optimization. And the adaptive facade control model is constructed based on the radio basis function neural network. And adopting a control system based on Gaussian prime model combined with adaptive facade control model, real-time calculation of the relative optimal solution of adaptive facade from facade form for different outdoor weather conditions. The results show that the adaptive facade can improve the indoor daylight performance and control the indoor glare risk. And the premise of not causing glare in the office area, it can increase the solar radiation and reduce the building's heating energy consumption. And this is the final plan. As the last part, and the topic of optimization for green building design has seen a significant interest and advancement in recent years, particularly as artificial intelligence tools are becoming more accessible and widespread. With the continuous development of the AI algorithm and tools in the construction industry, and the new technologies and the new tools we can obtain are becoming more diverse. And that's my presentation. Thank you.
Thank you, Professor Han. I think it's very nice to show us your technology, your software, and how you actually use that in a real